Welcome back. In this video, I will be taking you through certain problems on interference, particularly on the topic of division of wavefront, which includes primarily Young's double slit experiment and biprism. Alright, in this slide, I am showing a schematic diagram of the Young's double slit experimental setup. Note, small d is the distance between the two slits. Capital D is the distance between the plane of the slits and the screen where the interference pattern is observed, and lambda is the wavelength of the monochromatic light that is incident on the slits. The main formulas that we use for problems on Young's double slit experiment is shown in this slide. To begin with, the ratio of the amplitudes of the two waves that strike the slits S1 and S2 is given by R is equal to A1 by A2. The width of the slits is proportional to the intensity of the waves that strike the slits, and as intensity is proportional to amplitude squared, we can write W1 by W2 equal to I1 by I2, which is nothing but A1 by A2 whole squared or R squared. One of the major formulas that we use is the ratio of the maximum intensity to the minimum intensity in the interference pattern, I max by I minimum, which is given by R plus 1 divided by R minus 1 whole squared. There is another formula which is very useful to calculate the intensity at any point on the screen in terms of the individual intensities produced by the two waves at that point and the phase difference between them. As shown in the slide, capital I, which is the intensity at any point in the screen due to the superposition of the two waves starting from S1 and S2, is given by I1 plus I2 plus 2 times root of I1 times I2 times cos delta, where I1 and I2 are the intensities produced at that point by the two waves individually, and delta is the phase difference between them. Finally, probably the most important formula in this chapter is the fringe width. The fringe width is nothing but the distance between successive bright fringes or successive dark fringes, and this is given by beta equal to lambda times capital D by small d, where lambda is the wavelength of light, capital D is the distance between the slits and the screen, and small d is the distance between the slits. There is yet one more formula that we sometimes use. If we introduce a transparent medium of thickness T and refractive index N in the path of one of the interfering beams, then the entire fringe pattern will shift in the direction of this medium by S is equal to capital D by D times N minus 1 into T, where N is the refractive index of the medium. This is called the shift in the interference pattern. In this slide, we have shown the schematic representation of the fringe formation by a biprism. The angle of the biprism gamma is the angle made by the two refracting surfaces of the biprism. It is of the order of 178 to 179 degrees. The angle alpha, which is the angle made by one of the refracting faces with the base of the biprism, is given by the formula alpha is equal to 180 degree minus gamma divided by 2. Note that A is the distance of the biprism from the slit which is illuminated with light of monochromatic wavelength lambda, while B is the distance of the focal plane of the microscope where the fringe pattern is observed from the biprism. Clearly, A plus B is equal to D, which is the distance of the slit to the focal plane of the microscope. Now, if we introduce a convex lens between the biprism and the focal plane of the microscope where the fringes are observed, by moving the convex lens in one position, we would see two diminished images of the coherent sources S1 and S2. If the distance between the two diminished images of the coherent sources is D1, then when we move the convex lens farther apart, in another position, the two coherent sources would appear to be at a distance of D2 from one another. This would be an enlarged image of the coherent sources. One can show that the distance between the coherent sources D is equal to square root of D1 times D2. It is also possible to write this distance D in terms of the refractive index of the material of the biprism the distance between the biprism and the slit and the angle alpha. This formula shown in the slide is D equal to 2 times A into n minus 1 times R. Before commencing the problems, let us recall that I will be using the URAS method of solving physics problem. The 4 steps are understanding the problem, that means determining what is the data given and what is to be found out and what data can be assumed. The step R means recollecting the correct formula or recalling the correct mathematical relation between the known and the unknown quantities. A means arranging, that means rearranging the recalled formula such that the unknown terms are on one side and the known terms are on the other side. And finally, S means substituting the values in proper system of units, in our case SI, and simplifying and solving the problem. Now all the problems I have chosen are straightforward problems which involve only numerical substitution and simplification. So let's look at the first problem. It says two coherent sources have intensities in the ratio 25:16. Find the ratio of the intensities of the maxima to minima in the interference pattern. So the data given obviously is that I1 by I2 is equal to 25/16 and we have to find I max by I minimum. Recall that we can write R, which is the ratio of the root of the intensities I1 to I2, as 5/4. Now we know that I max by I minimum is nothing but R plus 1 divided by R minus 1 whole squared. So substituting for R and simplifying, we obtain I max by I minimum as 81 divided by 1, which can be written as 81:1. In this problem, the problem states that in Young's double slit experiment, the ratio of the intensities of the maxima to the minima is 25:9, and we are asked to find the ratio of the width of the two slits. You will recall that the ratio of the slit width W1 by W2 is actually I1 by I2 or A1 by A2 whole squared. But since R is equal to A1 by A2, the correct solution would be to write W1 by W2 is equal to R squared. So we need to find out R. The data given to us is I max by I minimum. We know that I max by I minimum, which is 25/9, is equal to R plus 1 divided by R minus 1 whole squared. So taking square roots on both sides, we get R plus 1 by R minus 1 is equal to 5/3, and solving for R, we obtain R is equal to 4. Therefore, W1 by W2 would be equal to R squared, which is 16/1. This problem is straightforward. It is based on finding the intensity at a point on a screen in a double slit experiment, knowing the intensities produced by individual waves and the phase difference between them. The problem reads that two coherent beams of wavelength 5000 angstrom unit reaching a point individually produce intensities of 1.44 and 4 units. If they reach together, then due to superposition, the intensity is 0.9 units. Calculate the lowest phase difference with which the beams reach the point. Well, the formula is straightforward. I is equal to I1 plus I2 plus 2 times root of I1 I2 multiplied by cos delta. We are given I1 and I2 and we also know I, so we need to find delta. So substituting the values of I1 and I2, we solve for cos delta as minus 0.9458, which yields delta is equal to cos inverse of minus 0.9458, which is 161.04 degree. Note that sometimes in a problem, some data that is given to you is superfluous or redundant. In this problem, the wavelength of light is not used in solving the problem. So this is something that you must bear in mind, that not all data are sometimes necessary to solve the problem. Problem number 4. Laser light of 630 nanometer is incident on a pair of double slits and produce an interference pattern in which the bright fringes are separated by 8.1 millimeter. A second source produces an interference pattern in the same setup in which the dark fringes are separated by 7.2 millimeter. Calculate the wavelength of the second source. So the data given is lambda 1 equal to 630 nanometer, that is the wavelength of the first source. The point to understand is that fringe width is the distance between two successive bright fringes or two successive dark fringes in an interference pattern, and this will be equal to each other because interference fringes are equally spaced. So the fringe width with wavelength lambda 1, that is 630 nanometer, is beta 1 equal to 8.1 millimeter. We are asked to find what will be the wavelength of light if the fringe width in the same setup is 7.2 millimeter. So the second point to understand in the understanding step is, when you say same setup, it means the distance between the slits is not changed and the distance between the screen and the slits is also not changed. So basically we look at the formula beta equal to lambda capital D by D, and we note that capital D and small d are constant in this problem. Therefore beta is basically proportional to lambda. Hence I can write beta 2 by beta 1 is equal to lambda 2 by lambda 1. The next step is very straightforward. We can substitute directly for beta 2 and beta 1. Note that I have substituted in the same unit, namely millimeter. There is no need to convert into meter because the conversion factor 10 to the power of minus 3 will cancel anyway. On the right hand side, I have lambda 2 divided by 630 nanometer. So solving for lambda 2, we obtain the answer as 560 nanometer. So this kind of problem is very important for exam, where you need to look at a formula and try to understand the factors on which a particular parameter depends. Okay, here is the first problem on biprism. The problem statement is as follows, that the distance between the slit and biprism, recall it is A, and between the biprism and screen, recall that should be B, is 0.5 meter each. If the angle of the biprism is 179 degree and its refractive index is 1.5, find the wavelength of light used, given the distance between successive fringes is 0.0135 centimeter. The problem is very straightforward. However, there are a few points to be noted. First of all, conversion. The distance between successive bright fringes means beta. So beta is 0.0135 centimeter. If you shift 2 decimal place, it will be to the right, it becomes 1.35 into 10 to the power of minus 2 centimeter. Converting centimeter to meter, you have an additional 10 to the power of minus 2. So beta is 1.35 into 10 to the power of minus 4 meter in SI system. The second point to note is capital D is A plus B, and since each one of the distance A and B is 0.5 meter or 50 centimeter, so A plus B would be 100 centimeter or 1 meter. Then the refractive index of the prism is given as 1.5. Now we need to know the angle alpha. Alpha is nothing but 180 minus the angle of the biprism, which is 179, divided by 2. Now alpha works out to be 0.5 degree. It's important to understand that in the formulas that we use, we have to use the angle generally in radian measure if you have to work in SI system. So angle alpha would be pi by 360 radian. How did we get that? We know that 1 degree in angle measure is equal to pi by 180 radian. Therefore 0.5 degree would be pi by 180 into 0.5. Now the formula for beta is lambda into capital D by D. If you rearrange it, you get lambda is equal to beta into small d by capital D. Now if you look at the data given to us, beta is given to us, capital D is also given to us, but small d is not given to us. So we have to now recall another formula for small d in terms of two other data that we know, namely alpha and the refractive index n. If you recall, small d can be written as 2 times a into n minus 1 into alpha. So that is straightforward. We substitute for a, n and alpha, and remember alpha in radian, and obtain d is equal to 4.36 into 10 to the power of minus 3 meter. So once you have small d, you have all the data necessary to calculate lambda, and therefore we substitute in the formula lambda is equal to beta times small d by capital D and simplify to obtain lambda is equal to 5886 angstrom. Coming to problem number 6. The problem statement reads that the interference fringes are produced by a Fresnel's biprism in the focal plane of a microscope which is 1 meter from the slit. That means capital D is 1 meter. A convex lens is inserted between the biprism and the microscope. It gives two images of the slits in two positions. In one case, the two images of the slit are 4.5 millimeter apart, and in the second case, it is 2.90 millimeter apart. If sodium light of wavelength 5893 angstrom is used, find the fringe width. So the problem statement is rather direct. Capital D is 1 meter. Wavelength of light is 5893 angstrom, which is 5893 into 10 to the power of minus 10 meter. The distance between the two coherent sources in two positions of the lenses are given. That is, D1 is equal to 4.5 millimeter and D2 is equal to 2.9 millimeter. We are asked to find the fringe width. Now, obviously, we know that small d is equal to root of D1 into D2. So, substituting for D1 and D2, we obtain small d as 3.61 millimeter, which is converted to 3.61 into 10 to the power of minus 3 meter. Note that this is the most important recall step. Once you know what is small d, the rest is straightforward. Beta is equal to lambda into capital D by small d. Lambda, capital D and small d, all the three quantities are now known. So we substitute in SI unit and obtain the answer of beta as 1.632 into 10 to the power of minus 4 meter. Okay, ನಾನು ಈಗಾಗಲೇ ಹಲವಾರು ಪ್ರಾಬ್ಲಮ್ಗಳಲ್ಲಿ ಫಸ್ಟ್ ಸ್ಟೆಪ್ ಈಸ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ದ ಪ್ರಾಬ್ಲಮ್ ಅಂತ ಹೇಳ್ತೀನಿ. ಸೊ ವಾಟ್ ಈಸ್ ದಿಸ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡಿಂಗ್? By now you would have realized that understanding really means reading the problem and figuring out what is given to you and what is to be found out. So ಇದನ್ನ ಈ ಪ್ರಾಬ್ಲಮ್ ಅಲ್ಲಿ ಸೆಂಟೆನ್ಸ್ ಬೈ ಸೆಂಟೆನ್ಸ್ ತಗೊಂಡು ಮಾಡೋಣ. ಓಕೆ, ಪ್ರಾಬ್ಲಮ್ ಅನ್ನು ಓದೋಣ. In a biprism experiment with sodium light, fringes of width 0.0195 centimeter are observed 1 meter away from the slit. ಈ ವಾಕ್ಯನ ಕೇರ್ಫುಲ್ ಆಗಿ ಓದಿದಾಗ ಎರಡು ಇನ್ಫಾರ್ಮೇಷನ್ ನಮಗೆ ಗೊತ್ತಾಗುತ್ತೆ. ಮೊದಲನೇದು, ಫ್ರಿಂಜಸ್ ಆಫ್ ವಿತ್ 0.0195 ಸೆಂಟಿಮೀಟರ್ ಅಂದರೆ ಫ್ರಿಂಜ್ ವಿತ್. ಸೊ ಫಸ್ಟ್ ಡೇಟಾ ಗಿವನ್ ಇಸ್ ಬೀಟಾ ಇಸ್ ಈಕ್ವಲ್ ಟು 0.0195 ಸೆಂಟಿಮೀಟರ್. ಅದನ್ನು ಮೀಟರ್ ಲೆಕ್ಕದಲ್ಲಿ ಬರೆದ್ರೆ 1.95 ಇಂಟು 10 to the power of minus 4 ಮೀಟರ್. ಅದೇ ವಾಕ್ಯದ ಎರಡನೇ ಭಾಗ ನೋಡಿದ್ರೆ ಫ್ರಿಂಜಸ್ ಆಫ್ ವಿತ್ 0.0195 ಸೆಂಟಿಮೀಟರ್ ಆರ್ ಅಬ್ಸರ್ವ್ಡ್ 1 ಮೀಟರ್ ಅವೇ ಫ್ರಮ್ ದ ಸ್ಲಿಟ್ ಅಂತ ಹೇಳ್ತಾ ಇದ್ದಾರೆ. ಅಂದರೆ ಡಿಸ್ಟೆನ್ಸ್ ಡಿ ಈಸ್ 1 ಮೀಟರ್. ಸೊ 2 ಇನ್ಫಾರ್ಮೇಷನ್ ಬಂತು. ಈಗ ಎರಡನೇ ವಾಕ್ಯನ ಓದೋಣ. ಆನ್ ಇಂಟ್ರಡ್ಯೂಸಿಂಗ್ ಎ ಕಾನ್ವೆಕ್ಸ್ ಲೆನ್ಸ್ 0.3 ಮೀಟರ್ ಫ್ರಮ್ ದ ಸ್ಲಿಟ್, ಅಂದರೆ ಸ್ಲಿಟ್ಟಿಂದ 0.3 ಮೀಟರ್ ದೂರದಲ್ಲಿ ಒಂದು ಕಾನ್ವೆಕ್ಸ್ ಲೆನ್ಸನ್ನು ಇಂಟ್ರಡ್ಯೂಸ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ. ನಿಮ್ಮ ಲೋವರ್ ಕ್ಲಾಸಸ್ಸಲ್ಲಿ ನಿಮಗೆ ಇದನ್ನು ಕಲ್ತಿರ್ತೀರ. ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ ದಿ ಆಬ್ಜೆಕ್ಟ್ ಫ್ರಮ್ ದ ಲೆನ್ಸನ್ನು ಆಬ್ಜೆಕ್ಟ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಂತೀವಿ. ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ ದ ಇಮೇಜ್ ಫ್ರಮ್ ದ ಲೆನ್ಸನ್ನು ಇಮೇಜ್ ಡಿಸ್ಟೆನ್ಸ್ ಅಂತೀವಿ. ಸೊ ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಲೆಕ್ಕದಲ್ಲಿ ಆ ಎರಡು ಸ್ಲಿಟ್ಸ್ ಏನಿದೆ, ಆ ಎರಡು ಸ್ಲಿಟ್ಸೇ ನಮ್ಮ ಆಬ್ಜೆಕ್ಟ್ ಆಗುತ್ತೆ. ಸೊ ಆನ್ ಇಂಟ್ರಡ್ಯೂಸಿಂಗ್ ಅ ಕಾನ್ವೆಕ್ಸ್ ಲೆನ್ಸ್ 0.3 ಮೀಟರ್ ಫ್ರಮ್ ದ ಸ್ಲಿಟ್ ಅಂದರೆ ಆಬ್ಜೆಕ್ಟ್ ಡಿಸ್ಟೆನ್ಸ್ ಇಸ್ 0.3 ಮೀಟರ್ ಅನ್ನೋದು ಗೊತ್ತಾಗುತ್ತೆ, ಅಥವಾ ಯು ಇಸ್ 0.3 ಮೀಟರ್. ಸಿಂಪಲ್ ತಾನೆ. ಎರಡನೇ ಭಾಗಕ್ಕೆ ಬಂದರೆ 2 images of the slit are seen 0.7 centimeter apart. Now 2 images are seen ಅಂದಾಗ ನಾವು ನೋಡ್ತಿರೋದು ಇಮೇಜು. Now you will also recall from your pre-university classes that we can talk of the size of an object and the size of the image. ನಾವು ಈ ಲೆಕ್ಕದಲ್ಲಿ ಈ ಎರಡು ಸ್ಲಿಟ್ಸ್ ಏನಿದ್ದಾವೆ, ಎರಡು ಕೋಹರೆಂಟ್ ಸೋರ್ಸಸ್ ಅದು ಆ್ಯಕ್ಚುಲಿ, ಆ ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದಮ್ಮನ್ನು ನಾವು ಆ ಪರ್ಟಿಕ್ಯುಲರ್ ಡಿಸ್ಟೆನ್ಸನ್ನು ನಾವು ಒಂದು ಆಬ್ಜೆಕ್ಟ್ ಅಂತ ಬಳಸಿದ್ರೆ ಆ ಎರಡು ಸ್ಲಿಟ್ಟಿನ ಇಮೇಜು ನಮಗೆ 0.7 ಸೆಂಟಿಮೀಟರ್ ಅಪಾರ್ಟ್ ಕಾಣ್ತಿದೆ. ಅಂದರೆ ಸೈಜ್ ಆಫ್ ದ ಇಮೇಜ್ ಇಸ್ 0.7 ಸೆಂಟಿಮೀಟರ್. ಸೊ ಇಮೇಜ್ ಸೈಜನ್ನು ಕ್ಯಾಪಿಟಲ್ ಐ ಅಂತ ಬರೆದ್ರೆ ಇಟ್ ಈಸ್ 0.7 ಸೆಂಟಿಮೀಟರ್. ಮತ್ತು ಇಟ್ ಈಸ್ ಅಟ್ ಎ ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ 1 ಮೀಟರ್ ಫ್ರಮ್ ದ ಸ್ಲಿಟ್ ಅನ್ನೋದು ಆಗಲೇ ಫಸ್ಟ್ ಸೆಂಟೆನ್ಸಲ್ಲಿ ಬಂತು. ಇವಾಗ ಮೂರನೇ ಸೆಂಟೆನ್ಸ್ ಏನು ಹೇಳ್ತಾ ಇದೆ? ಕ್ಯಾಲ್ಕುಲೇಟ್ ದ ವೇವ್ ಲೆಂತ್ ಆಫ್ ಲೈಟ್ ಎಮಿಟೆಡ್ ಬೈ ದ ಸೋಡಿಯಂ ವೇಪರ್ ಲ್ಯಾಂಪ್. ಇದು ಸುಲಭ. ಲ್ಯಾಂಬ್ಡಾ ಇಸ್ ಈಕ್ವಲ್ ಟು ಎಷ್ಟು ಅಂತ. ಇವಾಗ ಏನೇನನ್ನು ರೀಕಾಲ್ ಮಾಡಬೇಕು? ನಾವು ಎರಡನೇ ಸೆಂಟೆನ್ಸಲ್ಲಿ ಕೇರ್ಫುಲ್ಲಾಗಿ ಓದಿದ್ರೆ ಅದರ ಲಾಸ್ಟ್ ಭಾಗ ನೋಡಿ. ಆನ್ ಇಂಟ್ರಡ್ಯೂಸಿಂಗ್ ಅ ಕಾನ್ವೆಕ್ಸ್ ಲೆನ್ಸ್ 0.3 ಮೀಟರ್ ಫ್ರಮ್ ದ ಸ್ಲಿಟ್, 2 images of the slit are seen 0.7 centimeter apart at a distance of 1 meter from the slit. ಸೊ ಈ ಇಮೇಜು ಸ್ಲಿಟ್ಟಿಂದ ಎಷ್ಟು ದೂರದಲ್ಲಿ ಕಾಣ್ತಿದೆ? 1 ಮೀಟ್ರಲ್ಲಿ ಕಾಣ್ತಿದೆ. ಲೆನ್ಸಿಂದ ಆಬ್ಜೆಕ್ಟಿಗೆ ಅಥವಾ ಸ್ಲಿಟ್ಸಿಗೆ ಡಿಸ್ಟೆನ್ಸ್ ಎಷ್ಟು? 0.3 ಮೀಟರ್. ಸೊ ಲೆನ್ಸಿಂದ ಇಮೇಜ್ಗೆ ಅಂದರೆ ಇಮೇಜ್ ಡಿಸ್ಟೆನ್ಸ್ ಎಷ್ಟಿರಬೇಕು? ಸ್ವಲ್ಪ ಯೋಚನೆ ಮಾಡಿ. ವೆರಿ ಸಿಂಪಲ್ ಅಲ್ವೇ? u plus v must be equal to 1 meter, therefore v must be equal to 0.7 meter. ಸೊ ನಮಗೆ ಮೊದಲನೇದಾಗಿ ಇಲ್ಲಿ ನಮಗೆ u plus v equal to 1 meter ಇಂದ v ಲೆಕ್ಕ ಬಂತು. ಇವಾಗ ಈ ಪ್ರಾಬ್ಲಮಲ್ಲಿ ನಾವು ಒಂದು ಇಂಪಾರ್ಟೆಂಟ್ ಕಾನ್ಸೆಪ್ಟನ್ನ ರೀಕಾಲ್ ಮಾಡಬೇಕು. ಕಾನ್ವೆಕ್ಸ್ ಲೆನ್ಸಿಗೆ ಒಂದು ಪ್ರಾಪರ್ಟಿ ಇದೆ. ಸೈಜ್ ಆಫ್ ದ ಇಮೇಜ್ ಬೈ ಸೈಜ್ ಆಫ್ ದಿ ಆಬ್ಜೆಕ್ಟ್ ಈಸ್ ಈಕ್ವಲ್ ಟು ಇಮೇಜ್ ಡಿಸ್ಟೆನ್ಸ್ ಬೈ ಆಬ್ಜೆಕ್ಟ್ ಡಿಸ್ಟೆನ್ಸ್. ಸೊ ನಾವಿಲ್ಲಿ ಸೈಜ್ ಆಫ್ ದಿ ಇಮೇಜ್ 0.7 ಸೆಂಟಿಮೀಟರ್ ಅಂತ ನೋಡಿದ್ವಿ. ಸೈಜ್ ಆಫ್ ದಿ ಆಬ್ಜೆಕ್ಟ್ ಕಂಡುಹಿಡಿಬೇಕು, ವಿಚ್ ಇಸ್ ಆ್ಯಕ್ಚುಲಿ ದ ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದ ಟೂ ಸ್ಲಿಟ್ಸ್ ಅಥವಾ ಆ್ಯಕ್ಚುಯಲ್ ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದ ಟೂ ಸೋರ್ಸಸ್ ಅಂತ ಹೇಳ್ಬೋದು, ವಿಚ್ ಇನ್ಸಿಡೆಂಟ್ಲಿ ವಿಲ್ ಬಿ ಸ್ಮಾಲ್ ಡಿ. ಸೊ ಅದನ್ನು O ಅಂತ ಇಟ್ಕೊಳ್ಳೋಣ. ಸೊ 0.7 ಸೆಂಟಿಮೀಟರ್ ಬೈ O ಮಸ್ಟ್ ಬಿ ಈಕ್ವಲ್ ಟು V ಇಸ್ 0.7 ಮೀಟರ್, U ಇಸ್ 0.3 ಮೀಟರ್. ಇದರಿಂದ ನಮಗೆ O ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದ ಟೂ ಕೊಹರೆಂಟ್ ಸೋರ್ಸಸ್, ವಿಚ್ ಇಸ್ ಆಲ್ಸೋ ನಥಿಂಗ್ ಬಟ್ ಸ್ಮಾಲ್ ಡಿ ಸಿಕ್ಕುತ್ತೆ, which is nothing but 3 into 10 to the power of minus 3 meter. So once you get this step, the rest is very straightforward. Since you know small d, you know capital D, and you also know beta, we can use the formula beta equal to lambda capital D by small d. Rearrange ಮಾಡಿಕೊಂಡು lambda is equal to beta into small d by d ಅಂತ ಫಾರ್ಮುಲಾ ಅಲ್ಲಿ ಬೀಟಾ, ಸ್ಮಾಲ್ ಡಿ ಮತ್ತು ಕ್ಯಾಪಿಟಲ್ ಡಿ ಮೂರಕ್ಕೂ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿ ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿದಾಗ ನಮಗೆ 5850 ಆಂಗ್ಸ್ಟ್ರಾಂಗ್. Now you must be very clear that it's not that in every problem you recall a formula, substitute the numbers and simplify to get the answer. There will be several problems where after recalling the formula we need to analyze the formula and adapt it suitably to the context of the problem. Problem number 8 is one such problem. The statement of the problem says, let's go sentence wise. A Fresnel biprism is set with sodium light of wavelength 5893 angstrom unit. This is straightforward. You have a biprism experiment in which the source is sodium light and it gives you a wavelength of 5893 angstrom unit. So lambda 1 is 5893 angstrom unit. The second sentence says, in the field of view of the eyepiece of the microscope, we observe 62 fringes. Now what is field of view? We know that the fringes are seen in the focal plane of the microscope. The field of view is the horizontal distance in which the fringes are seen. So if this field of view or horizontal distance is given to us and the number of fringes is also given to us, what do you think we can find from this? Obviously, if you divide the length of the field of view by the number of fringes, you would get the fringe width. So the second sentence says, in a particular field of view, there are 62 fringes. Then now let's come to the third one. The third sentence, I mean. The third sentence says, how many fringes will be seen in the same field of view if we replace the mercury source with a sodium source using a green filter of wavelength 5461 angstrom unit? That means, if we use light of wavelength 5461 angstrom unit in the same experimental setup, how many fringes are going to be seen in the same field of view? The phrase same field of view is important. Now you will obviously remember that beta, the fringe width, is proportional to the wavelength. So if the wavelength of light changes, fringe width should also change. Now if you have the same length or field of view length, if the fringe width changes, number of fringes will also change. Now we can actually hazard a guess here. Since beta is equal to or rather proportional to lambda, if lambda decreases, one would expect beta to decrease. If beta decreases, then what should happen to the number of fringes in the same field of view? Think about this. Let's come back to the problem. So let's assume that the length of the field of view is L and the number of fringes seen in that length is N. Therefore, we can write in general beta is equal to L by N. Or cross multiplying, we can write L is equal to beta into N. Now since L is constant, beta into N must be constant. Substituting for beta as lambda into capital D by small d, we can rearrange the formula and show that N into lambda, where N is the number of fringes and lambda is the wavelength of light, must be equal to small d divided by capital D into L. Note that this quantity small d divided by capital D into L is a constant. So what we have realized is that the product N into lambda must be constant. That means n1 lambda 1 must be equal to n2 lambda 2. Now you can answer the question I posed earlier in this slide. That means if lambda decreases, one would expect this n to increase. Let's see if you get that answer. So substituting for n1 and lambda 1, which is 62 and 5893 Armstrong unit, we need to find n2. Lambda 2 is of course 5461 Armstrong. When you solve for n2, you get 67. Of course, remember, you may not get an exact integer 67. One has to round off to the nearest integer. So this kind of problems are important in the exam because they are not direct substitution problem. You have to recall a formula and then try to analyze the formula and adapt the formula to the context of the problem. This problem is rather straightforward. It's based on the formula beta is equal to lambda into capital D by small d. However, we won't be directly substituting the values of capital D and small d. Instead, capital D and small d will be written in terms of other parameters associated with the biprism. I urge you to go back to the second slide or third slide, I think, which shows the biprism and the schematic representation of the various distances involved with the biprism. Now let's come back to the problem. It states that the inclined faces of the biprism of refractive index 1.5 makes an angle of 2 degrees with its base. It's straightforward. Refractive index is 1.5 and alpha is 2 degree. The slit is illuminated by monochromatic light is placed at a distance of 10 centimeter from the biprism. Andre biprism in the slit ಗೆ distance ಅನ್ನ 10 centimeter ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ. ಹಂಗಂದ್ರೆ A is equal to 10 centimeter ಅಥವಾ 0.1 meter. Next sentence is very important to understand. This is where I said in an earlier slide that the language should not be a hindrance to solving the problem. English language ಮತ್ತು ಕನ್ನಡದಲ್ಲಿ ಈ ಆಬ್ಜೆಕ್ಟ್ ಮತ್ತು ಸಬ್ಜೆಕ್ಟ್ ಇವು ಡಿಫ್ರೆನ್ಸ್ ದಿ ವೇ ಇಟ್ ಈಸ್ ಯೂಸ್ಡ್ ಕ್ಯಾನ್ ಬಿ ಡಿಫ್ರೆಂಟ್. ಸೊ ಈ ಸೆಂಟೆನ್ಸ್ ಏನು ಹೇಳುತ್ತೆ, ಇಫ್ ದ ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ಟೂ ಸಕ್ಸೆಸಿವ್ ಡಾರ್ಕ್ ಫ್ರಿಂಜಸ್ ಅಬ್ಸರ್ವ್ಡ್ ಅಟ್ ಅ ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ 1 meter ಫ್ರಮ್ ದ ಬೈಪ್ರಿಸಮ್ ಈಸ್ 0.18 millimeter, ಫೈಂಡ್ ದ ವೇವ್ ಲೆಂತ್ ಆಫ್ ಲೈಟ್. ಅಂದರೆ ಸೆಂಟೆನ್ಸಲ್ಲಿ ಏನು ಹೇಳ್ತಾ ಇದ್ದಾರೆ, ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ಸಕ್ಸೆಸಿವ್ ಡಾರ್ಕ್ ಫ್ರಿಂಜ್ ಅಂದರೆ ಫ್ರಿಂಜ್ ವಿಡ್ತು. ಫ್ರಿಂಜ್ ವಿಡ್ತಿನ ಬೆಲೆ ಎಷ್ಟು? ಇದು 0.18 millimeter ಆಗುತ್ತೆ. ಆ್ಯಂಡ್ ಈ ಫ್ರಿಂಜಸ್ ಎಲ್ಲಿ ನೋಡ್ತಾ ಇದ್ದೀವಿ? ಇಟ್ ಈಸ್ ಅಬ್ಸರ್ವ್ಡ್ ಅಟ್ ಎ ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ 1 meter ಫ್ರಮ್ ದ ಬೈಪ್ರಿಸಮ್. ಅಂದರೆ ಫೋಕಲ್ ಪ್ಲೇನ್ ಆಫ್ ದ ಮೈಕ್ರೋಸ್ಕೋಪ್ಗೂ ಬೈಪ್ರಿಸಮ್ಗೂ ಡಿಸ್ಟೆನ್ಸ್ 1 meter. ಇನ್ ಅದರ್ ವರ್ಡ್ಸ್ ಬಿ ಈಸ್ ಈಕ್ವಲ್ ಟು 1 meter. ಇದನ್ನು ಸ್ವಲ್ಪ ಕಾಮನ್ ಸೆನ್ಸಿಂದ ಕೂಡ ಬಿ ಈಸ್ 1 meter ಆ್ಯಂಡ್ ಬೀಟಾ ಈಸ್ 0.18 millimeter ಅಂತ ನೀವು ತಿಳ್ಕೊಬೋದು. ಬೀಟಾ ವಿಲ್ ಬಿ ವೆರಿ ಸ್ಮಾಲ್. ಇಟ್ ಕೆನಾಟ್ ಬಿ ಆಫ್ ದಿ ಆರ್ಡರ್ ಆಫ್ 1 meter. ಯೂಶ್ವಲ್ ಮಿಸ್ಟೇಕ್ಸ್ ಈ ಸೆಂಟೆನ್ಸಲ್ಲಿ ಏನು ಮಾಡ್ತಾರೆ ಅಂದರೆ ಸ್ಟೂಡೆಂಟ್ಸು ಬೀಟಾನ 1 meterಗೂ ಮತ್ತು ಸ್ಮಾಲ್ ಬಿ ಅದನ್ನು 0.18 millimeter ಹಾಕ್ಕೊಂಡ್ಬಿಡ್ತಾರೆ. ಆ ಮಿಸ್ಟೇಕನ್ನು ಮಾಡಬೇಡಿ. ಸೊ ಡೇಟಾ ಎಲ್ಲ ಕೊಟ್ಟಿದ್ದಾರೆ. ಓನ್ಲಿ ಥಿಂಗ್ ಇಸ್ ದಟ್ ಆಲ್ಫಾ ಶುಡ್ ಬಿ ಕನ್ವರ್ಟೆಡ್ ಟು ರೇಡಿಯನ್. 2 degreeನ π/180 ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿ π/90 ರೇಡಿಯನ್ ಅಂತ ಹಾಕ್ಕೊಳ್ತೀವಿ. ಬೀಟಾ ಇಸ್ 0.18 millimeter. ಅದನ್ನು 1.8 × 10⁻⁻4 meter ಅಂತ ಹಾಕಿದ್ವಿ. ಸೊ ಫಾರ್ಮುಲಾ ಇಸ್ ಸ್ಟ್ರೇಟ್ ಫಾರ್ವರ್ಡ್. ರೀಕಾಲ್ ಸ್ಟೆಪ್ಪಲ್ಲಿ ಬೀಟಾ ಇಸ್ ಈಕ್ವಲ್ ಟು ಲ್ಯಾಂಬ್ಡಾ ಇಂಟು ಕ್ಯಾಪಿಟಲ್ ಡಿ ಬೈ ಸ್ಮಾಲ್ ಡಿ. ನೆಕ್ಸ್ಟ್ ರೀಕಾಲ್ ಸ್ಟೆಪ್ಪು ಕ್ಯಾಪಿಟಲ್ ಡಿಗೆ ಎ ಪ್ಲಸ್ ಬಿ ಅಂತ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ತೀವಿ ಮತ್ತು ಸ್ಮಾಲ್ ಡಿಗೆ 2 × a × n-1 × ಆಲ್ಫಾ. ಸೊ ಇಲ್ಲಿ ಎರಡು ಥರ ರೀಕಾಲ್ ಇದೆ. ಒಂದು ಬೇಸಿಕ್ ಫಾರ್ಮುಲಾ ಮತ್ತು ಫಾರ್ಮುಲಾ ಒಳಗಿರೋ ಪ್ಯಾರಾಮೀಟರ್ಸು ಕ್ಯಾಪಿಟಲ್ ಡಿ ಮತ್ತು ಸ್ಮಾಲ್ ಡಿ ಅವನ್ನು ಕೂಡ ರೀಕಾಲ್ ಮಾಡಬೇಕು ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ಎ, ಬಿ, ಆಲ್ಫಾ, ಎನ್ ಎಕ್ಸೆಟ್ರಾ. So now the problem is very straightforward. Beta is equal to lambda into a plus b divided by 2a into n-1 times alpha. Rearranging step ಬರುತ್ತೆ. Rearranging ಸ್ಟೆಪ್ಪಲ್ಲಿ ಈ ಫಾರ್ಮುಲಾನ ನಾವು ರೀಅರೇಂಜ್ ಮಾಡಿ lambda is equal to beta into 2a into n-1 into alpha divided by a plus b ಬರಿತೀವಿ. Rest I don't really have to explain. We substitute the values of all the quantities for lambda, solve and obtain the answer 5714. The last two problems are based on the shift in the interference pattern in a double slit experiment when we introduce a transparent plate of thickness T and refractive index N in the path of one of the beams. There is a straightforward formula. It's a matter of identifying the numbers and substituting. So the problem is straight away read as the central fringe of an interference pattern produced by light of wavelength 6000 Armstrong is shifted to the position of the fifth bright fringe by introducing a thin glass plate of refractive index 1.5. There are three things here. Remember that when you say the fringe pattern is shifted, each and every fringe is shifted by the same distance. Also, the shift is always in the direction in which the plate has been placed. So now going back to the first sentence, it says the central fringe of an interference pattern produced by light of wavelength 6000 angstrom. So lambda is 6000 angstrom unit, shifted to the fifth bright fringe, position of fifth bright fringe. Andre, the shift S is equal to 5 times beta. This is what you have to really understand. The rest is simple. And you are introducing a glass plate of refractive index 1.5. Find the thickness of the plate. So we know the formula that S is equal to capital D by small d into n minus 1 into T, where T is the thickness, n is the refractive index. And capital D and small d have their usual meaning. But capital D and small d can be written as ratio of beta by lambda. From the formula, beta is equal to lambda into capital D by d. So the formula to be used in the problem is S is equal to beta divided by lambda times n minus 1 times T. Now the LHS S is nothing but 5 beta. So when you substitute 5 beta is equal to beta times 1 minus 5 minus 1 times T divided by 6 into 10 to the power of minus 7, which is nothing but 6000 angstrom written in meter unit. Solve for T, we get 6 into 10 to the power of minus 6 meter. Note, sometimes 10 to the power of minus 6 meter can be written as a micron or a micrometer. Problem number 11 is also similar to problem number 10. We need to find the wavelength of light here instead of the thickness of the glass plate. That is all the difference. Otherwise, the formula is the same. In the rearranging step, instead of solving for T, we will now solve for lambda. So if you go back to the problem, it says a thin sheet of glass, refractive index 1.5 of thickness 6 micrometer, is introduced in the path of one of the interfering beams in a biprism experiment, shifts the central fringe to a position occupied by the sixth fringe. Find the wavelength of light. So here shift is 6 beta, n is 1.5, t is 6 micrometer. So if you recall from the formula that S is equal to beta by lambda into n minus 1 times T, we can rearrange it as T is equal to S into lambda divided by n minus 1 into beta, or lambda is equal to T into n minus 1 into beta divided by S. So we'll substitute for S as 6 beta, the rest of the numbers are substituted, and you solve for lambda as 5000. Okay, that brings us to the end of this video on problems on interference of light on Young's double slit experiment and biprism. Essentially, double slit experiment and biprism are based on interference of light by the division of wavefront. In the next video, I will look at problems of interference of light based on division of amplitude. We will discuss situations like interference by thin films, Newton's rings, etc. I would like to end this video by sincerely acknowledging Professor N. Manju Bhaskar. All the problems that was discussed in this book has been sourced from the textbook of physics for 4th semester of BSc course written by Professor N. Manju Bhaskar. The book is published by Scientific Thought Publication.